All right, welcome everyone. So let's continue working with eigenvectors and eigenvalues and eigenspaces and prove some nice general results. So here what I want to do is prove the following theorem, that if v1, v2, all the way up to vr are eigenvectors corresponding to distinct eigenvalues that lambda 1, lambda 2, up to lambda r for an n by n matrix A, then this set of vectors v1, v2, all the way up to vr is going to be a linearly independent set of vectors. So let's take a look at the proof of this theorem. So let's suppose we're going to prove this by contradiction. So let's assume the opposite of what we're trying to show, and we'll show that that is going to lead to a contradiction. So therefore, the original statement must be true. So let's suppose we have a set of vectors v1, v2 that are eigenvectors all the way up to vr. Let's assume this is linearly dependent, okay, the opposite of what we're trying to prove. So if I have a linearly dependent set, then you may recall from earlier, this means that there is some vector in this set, we'll call it vp plus 1, that can be written as a linear combination of all of the vectors that come before it. So there has to be some vector in this set, we'll call it the p plus 1 vector, that can be written as a linear combination of the p vectors that come before it in the set. So these constants, c1, c2, up to cp, they're all not equal to 0. Some of them may be 0, but all of them cannot be 0. And so now we're going to take this equation that I've labeled 1 up here, and we're going to multiply both sides of this equation by the matrix A. So multiplying the right side by matrix A gives us lambda p plus 1 times vp plus 1, because we're assuming vp plus 1 is an eigenvector for the eigenvalue lambda p plus 1. So what it means for lambda p plus 1 to be an eigenvalue, again, is that multiplying some non-trivial vector by the matrix A is equivalent to multiplying that same vector by the scalar lambda p plus 1. And applying this same property that all of these vectors v1, v2, up to vp are all eigenvectors for lambda 1, lambda 2, lambda p, if I multiply the right side of this equation on the left by matrix A, we can use the linearity property of matrix multiplication to write this as A times C1 V1, and A times C1 V1 is equal to C1 times A V1. And A V1 gives us lambda V1 because V1 is an eigenvector for lambda 1. So this first term, when I multiply it by A, simplifies to C1 times lambda 1 times V1. And this is going to be the case for each of these terms. So we're going to add up terms that look like this all the way up to the last term, which is going to be Cp lambda p times Vp. So now I know that this lambda p plus 1, Vp plus 1 has to equal all of this, because these, we started with an equation and we apply the same operation to both sides of those equations. And so next we can also go back to equation 1, and we can choose to multiply both sides of equation 1 by lambda p plus 1. So I'm going to multiply lambda p plus 1 times both sides. And then we're going to subtract the relations that we get from equation 1 when I multiply it by lambda p plus 1 from the resulting equation that we got, which was this is going to equal to this. We don't really care about that in the meantime. So I'm going to take this equation that I get when I multiply by lambda p plus 1 and subtract from it the equation that we have when I multiplied both sides by A. So subtracting the left sides, I would have lambda p plus 1 times vp plus 1. And I'm going to subtract from that the left side of equation 2, which is going to give me the 0 vector. And then I'm going to take lambda p plus 1 and also multiply it by every term on the right side of equation 1 and subtract from that the right side of equation 2. And so we're going to have a bunch of terms that look like C1, V1, lambda p plus 1, C2, V2, lambda p plus 1. And on this equation 2, the right side looks like C1, lambda 1, V1. So all of these terms, the first terms in both of these equations, are going to have a C1 and a V1. So I can rewrite the difference of the right sides as saying C1, V1 times lambda 1 minus lambda p plus 1. And I have C2, V2, and then we can group these two terms together and write that as lambda 2 minus lambda p plus 1. And we keep going all the way out to the pth term, which we could write as Cp times lambda p minus lambda p plus 1 times the vector Vp. So now we have another homogeneous equation, and we have assumed that this first set of vectors v1 up to vp is linearly independent. So we assumed that this set of vectors v1 to vr was linearly dependent. So that meant we assumed that vp plus 1 was the very first vector in this set that we're able to write as a linear combination of the previous vectors. So that would imply that all of the previous vectors can't be written as linear combinations of other vectors. So these first p vectors are linearly independent. So now I have a vector equation 0 is equal to linear combinations of v1, v2 up to vp. And we know that all of these lambdas are distinct. So lambda 1 minus lambda p plus 1 is non-zero. Lambda 2 minus lambda p plus 1 is non-zero, and so on. So because these vectors v1, v2 up to vp are linearly independent, the only solution to this equation would mean all of these weights in front of each of these vectors are 0. There's only a trivial solution. And since, again, we know that these differences of lambdas are all non-zero, that means the only solution to this equation is setting all of these weights, C1, C2, C3, all the way up to Cp. They must all equal 0. And here's where we get our contradiction. Namely, we assumed that Vp was a linear combination of the previous vectors v1 up to vp by choosing weights C1, C2, Cp that are all non-zero. So now we get a contradiction. By this assumption, we see that all of these weights, C1, C2 up to Cp, have to be 0. But by our initial assumption that this was a linearly dependent set, and therefore Vp could be written as a non-trivial linear combination of the previous p vectors in that set, we reach the contradiction because now we see that all of these vectors are 0, which is a contradiction. So therefore, this original assumption must be wrong, and the opposite, that this set of eigenvectors for distinct eigenvalues, v1, v2 up to vr, must be linearly independent as claimed by this theorem.